Till now we discussed the combinational circuits. In the combinational circuits, the output depends only on the present inputs of the circuit, so that it is possible to write output is the function of present inputs of the circuit. Whereas the sequential circuits, the output depends not only on the present inputs of the circuit, but also on the previous state of the circuit. So the difference what we are looking is, in the case of the combinational circuits, the output depends only on the present inputs of the circuit, whereas in the sequential circuit, the output depends a part of the present inputs of the circuit also on the previous state of the circuit. Once you are talking, the output depends even on the previous state. So to respond based on the previous state, the circuit is required to remember the previous state information. If the circuit is able to remember the previous state information, then only it is possible by the circuit to respond a part of the present inputs even based on the previous state of the circuit. So once the circuit is required to remember the previous state information, then in these circuits, to remember the previous state information, the circuit need to have some memory elements. If at all the circuit is having some memory elements to remember the previous state information, then only it is possible by the circuit to respond a part of the present inputs even on the previous state of the circuit. Such memory elements in the digital circuits are nothing but flip-flops. We are having standard flip-flops, SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. These are the standard flip-flops. Each one of these flip-flops can store 1 bit data. In all these flip-flops, one of the basic important component is binary latch. A binary latch is basically a cross-coupled inverter circuit. So this cross-coupled inverter circuit we are naming as binary latch. This cross-coupled inverter circuit operation is possible even by using NAND gates or even by using NOR gates. Let us try here by using NAND gates. Let us name it is the NAND gate N1, it is the NAND gate N2. The NAND gate N1 input is the NAND gate N2 output. The NAND gate N2 input is the NAND gate N1 output. So when we are connecting two such NAND gates like this, and whenever we are putting the power on, these two NAND gates may be taken even from the same IC chip. They may not be having the same propagation delay. It is a guarantee there will be some mismatching in the propagation delay of these two NAND gates. Because the difference in the propagation delay of two NAND gates, one of the NAND gate may be responding little fast as and when we are putting the power on. Suppose the NAND gate N1 is responding little fast with output of say 1. Then this 1 becomes the input of the NAND gate N2, so that N2 output becomes 0. Or if at all the NAND gate N1 is responding with output of 0, that becomes the input of the NAND gate N2, so that N2 output becomes 1. So the circuit is going to respond with the output may be 1 or with maybe output of 0. Of course, as and when we are saying the circuit output, default means it is referring to the gate N1 output. So default means in our total discussion of these flip-flops, whenever we are talking the circuit output or the flip-flop output or the binary latch output, it is default referring to the gate N1 output. So because of this, if at all we are naming the gate N1 output as Q, the gate N2 output will be naming as Q complement. So anyway, the circuit is responding maybe with the output of 1 or maybe with the output of 0. This output is available in the circuit as it is, as long as the power is on, so that the circuit is able to store 1 bit data. This circuit, of course, we are naming as the binary latch. And we are looking, the circuit is able to store a bit maybe 1 or 0, not as per the user need. It is storing a bit maybe 1 or bit maybe 0 based on the internal propagation delay difference between the gate N1 and N2. It is not storing as per the user need this 1 or 0. Basically, we are looking in the circuit, there is no user access. So basically what we are looking is, we are not having any user inputs in the circuit. So it required for us to provide the user inputs to the circuit. If at all we are providing user inputs to the circuit, then may be possible to store a bit maybe 1 or bit maybe 0 as per the user need. So to provide the user access in the circuit, it required for us to increase the hardware of this binary latch. This increased hardware binary latch circuits we are naming as flip-flops. One of the simplest way, few of the authors will mention the difference between the binary latch and flip-flop as the flip-flop is having always the user inputs, whereas the binary latch is not having the user inputs. So as I said, to provide the user inputs, we are increasing the hardware of this binary latch, or basically we are modifying the hardware of this binary latch. We are using here 2 more NAND gates. This let us name gate N3, and this gate let us name as gate N4. Gate N3 output is the input of the gate N1, gate N4 output is the input of the gate N2, and the gate N3 input let us name S input, gate N4 input let us name as R input. And this modified circuit we are renaming as SR flip-flop. We are naming this as SR flip-flop. If at all S is 1, R is 0. Having S is 1, the gate N3 output becomes 0. Having R is 0, gate N4 output becomes 1. From the knowledge of the NAND gates, if at all we are looking, the NAND gate may be with multiple inputs. Say for example, it is having this A, B, C are the inputs. If at all one of the NAND gate output is 0, without bothering the other inputs of the NAND gate, without knowledge of other inputs of the NAND gate, it is possible to look the NAND gate output is 1. And similarly, if at all one of the input of the NAND gate is 1, then of course we'll be having the response of the NAND gate based on the other 2 inputs. Based on the other 2 inputs, we are looking to the output of the NAND gate. So that as and when one of the input of the NAND gate is 0, without bothering about the other inputs, it is possible to write the output of the NAND gate is 1. And whenever one of the input of the NAND gate is 1, the output is depending upon other 2 inputs. So based on our description, it is depending upon A and C. So in other way, it is possible to speak, as and when one of the input of the NAND gate is 1, the output is independent of this particular input, and it is depending upon only on the other 2 inputs. So So with the knowledge of this NAND gate operation, it is easily possible for us to understand the operation of this circuit now. Based on S is 1, R is 0, we recognize gate N3 output is 0, N4 output is 1. Now we are looking one of the input of the NAND gate N1 is 0. Having N1, one of the input is 0, N1 output is possible to write as 1. It is happened so for gate N2 both the inputs are 1, so that N2 output is 0. Similar to this, if at all we are talking S is having the value as 0, R is the value of 1. If at all S is 0, R is 1, definitely we are going to recognize it is going to have the reverse outputs between gate N3, N4 and N1, N2. So N3 output will be 1, N4 output will be 0. Having one of the input of the NAND gate N2 is 0, N2 output is 1. Having both the inputs of the N1 is 1, N1 output is 0. So that to store a bit as a 1 in the circuit, S must be 1, R must be 0. To store a bit in the circuit is to be 0, S must be 0, R must be 1. So while modifying the hardware of this binary latch, we are able to recognize, we are able to store a bit in the circuit as per the user need. So this modified circuit, as I said, they are naming as SR flip-flop. So based on this discussion, we are recognizing whenever S is 0, R is 1, the circuit output is 0. And whenever S is 1, R is 0, the circuit output is 1. We know on S and R, apart of 0, 1 and 1, 0, we are having other possible combinations. S and R may be both zeros, or S and R may be both ones. Before going to use any device or any component, it is better to understand the operation of the component or the device corresponding to all possible inputs. Hence, we need to try to recognize the output of the circuit even because of 0, 0, even because of 1, 1. Let us try to look because of 0, 0 first. Consider, before applying any inputs, the gate N1 output is X, so that N2 output becomes X complement. Of course, X is nothing but a Boolean constant, maybe 0 or maybe 1. Now, if at all S is 0, R is 0. If at all S is 0, R is 0, gate N3 as well as gate N4 outputs are 1. So that gate N1 and N2, one of the input is 1. Whenever one of the input of the gate N1 or N2 is 1, based on our earlier description, while having one of the input of the NAND gate is 1, the NAND gate output depends on the other input. If at all other input is A, it is coming to be A complement. So based on this, it is possible to recognize the second input of the gate N2 is X, so that N2 will continue the same X complement. Other input of the gate N1 is X complement, so that N1 will continue the same X. So in other way, what is the previous output we are having, the same output will continue. So based on this, it is possible to write now, whenever S is 0, R is 0, the output of this flip-flop is same as the previous state. Similarly, let us try to recognize the output of the circuit because of 1, 1. Whenever S is 1, R is 1, gate N3 as well as N4 both will be having output is 0. So based on this, we are looking the gate N1 and N2 both must be the output of 1. Based on the cross-coupled connection, at any moment between the gate N1 and N2, we are not reading the same output. So between the N1 and N2, there it must be complementary output. Because of this 1, 1 output we are speaking, it is not allowed input. So we don't want to use this circuit whenever S and R both are 1. Based on this, we are speaking they are not allowed inputs. So this table what we developed, this we are naming as truth table of the circuit. While discussing the combinational circuits, we mentioned the combinational circuit operation is always under the control of a control enabled signal. As similar to the control enabled signal, even in the case of sequential circuit, the operation of the sequential circuit will be always under the control of a clock signal. By looking always the sequential circuit operation under the control of such a clock signal. The clock repetition time. In the sequential circuits, the major components of the flip-flops, we want to have the sequential circuit operation under the control of such a clock signal, then the components what we are having as a major components of the sequential circuits, they must operate under the control of such a clock signal. Hence, we need to take care to modify this circuit to incorporate a clock signal. So, to incorporate a clock signal in the circuit, it required first to take the gate N3 and N4 or two input 90 gates. The second input of the gate N3 and N4 is the common input. This common input we are naming as the clock signal. Now, in the presence of such a clock signal, we want to look to the operation of the circuit. Suppose consider it is nth clock pulse. Before applying this nth clock pulse, the circuit output let us name as Qn, so that after passing of this clock signal, the flip-flop output let us name as Qn plus 1. So based on this clock signal, it is possible to speak Qn is the previous state and Qn plus 1 is the next state. Using this terminology, let us try to read the truth table of this flip-flop. As long as clock is 0, whenever the clock is 0, without looking what is S, what is R, it is possible to read gate N3 and N4 both are 1. It was the same situation when S was 0, R was 0. So we recognize the state is same as the previous state. We recognize the output is the same as the previous state. So based on this, it is possible now using this terminology, what is the output we are going to read, it is the same as the previous state. And as and when clock is 1, as and when the clock is 1, as and when one of the input of the AND gate is 1, then AND gate output is depending upon the second input. With this knowledge, it is possible to look whenever the clock is 1, with 0, 0, it is same as the previous state. With 0, 1, it is 0. With 1, 0, it is 1. Anyway, this 1, 1 is not allowed. So it is the truth table we can read with this clock incorporation in the circuit. This modified circuit, to distinguish from the earlier SR flip-flop, we are naming as clocked SR flip-flop. In fact, all the sequential circuits operation is with respect to a clock signal. In fact, all the flip-flops which are practically available are with clock only. In fact, one of the other way to distinguish between the binary latch and the flip-flop is the flip-flop is having always a clock signal, whereas the binary latch is not having a clock signal. Few of the authors will speak the difference between the binary latch and the flip-flop like this. So flip-flop is having always a clock input, whereas the binary latch is not having a clock input. So even if you speak simply SR flip-flop, JK flip-flop without a prefix word of the clock, default we need to understand it is with respect to clock only. The circuit is always available, or operation is always with respect to clock only. So we are looking here, it is the truth table of this SR flip-flop. So in this circuit we are recognizing, if you want to read the circuit output is to be 0, then S must be 0, R must be 1. If you want to read the circuit output is to be 1, S must be 1, R must be 0. Of course, in the presence of the clock signal, these inputs are giving the effect. But sometimes it may be required without using such a clock signal, the flip-flop output we may want to read may be 0, or the flip-flop output we may want to read as a 1. So we want to read the flip-flop output without using a clock signal. A flip-flop without using a clock, or in the absence of the clock signal, the operation what we are going to look, that operation generally named as asynchronous operation. In the presence of the clock signal, what is the operation we will be looking, generally it is to be named as synchronous operation. Anyway, without using a clock signal, we may need a facility to read the flip-flop output may be 1 or flip-flop output may be as 0. To get such facility in the circuit, it required further modification in the hardware of this circuit. Further modification what we are doing in the hardware of this circuit is, we are taking gate N1 as well as gate N2 as 3 input NAND gates. The third input of gate N1 is preset input. The third input of the gate N2 is clear input. So with this modification, it is possible to look without using a clock signal the circuit output as the user need, possible to read maybe as a 1 or maybe as 0. So to recognize the operation of the circuit, let us develop a table here also. Clock, preset, clear, the flip-flop output Q. As I said, without using clock, so that the clock must be 0. So whenever the clock is 0, no need to talk about anything about S and R. Gate N3 and N4 both are 1. Later, let us keep preset 0, clear 1. While keeping preset 0, clear 1, it is possible to look for gate N1, output is 1. Having preset is 0, one of the inputs that indicate N1 is 0. Having one of the inputs that indicate N1 is 0, then indicate N1 output must be 1. Now, if you look to the N2, N2 is concerned, all the 3 inputs are 1, so that N2 output becomes 0. Hence, whenever preset 0, clear 1, the flip-flop output we are reading as 1. Similarly, whenever clear is 0, preset is 1, and of course clock is 0. Having clear 0, preset 1, the operation between the N1 and N2 will be reverse. Having one of the input of the gate N2 is 0, N2 output is 1. All the 3 inputs now for N1 are 1, so that N1 output is 0. So we are reading the circuit output as 0. Reading circuit output as 0 is called clear operation. Reading circuit output as 1 is called preset operation. So we are looking for this preset and clear operation. The clear and presets are not with the same values. We will be having between the clear and the preset always the complementary values. And for normal operation, the circuit operation must be based on S and R as and when we are applying the clock signal. So that for normal operation, clock must be 1, and for normal operation, the preset and clear should not give any effect. If you want to make any one of the input of the NAND gate is to be ineffective, that NAND gate input must be connected to 1. So based on this knowledge, it is possible to look for normal operation to see the operation of the flip-flop using S and R and clock. It required for us to use the preset and clear both as 1. So it is the required condition for normal operation of the circuit. This table sometimes we will be naming as asynchronous table because there is no use of the clock. Hence we are unable to speak it is an asynchronous table. Based on this, it's supposed to be named truth table, supposed to be named as synchronous table on this flip-flop. In this flip-flop, we are looking at a small problem. The problem is, whenever both the inputs are 1, 1, we are unable to predict what is the output. As I was talking somewhere in between, before going to use any device, any component, it is better to know the device response or component response corresponding to all possible inputs. Hence, it is better to try to see the response of the circuit even because of 1, 1. To see the flip-flop operation even because of 1, 1, then we need further modification in the hardware of this circuit. The modification what we are doing in this circuit is, are taking the gate N3 as well as the gate N4 both as 3 input NAND gates. The third input of the gate N3 is Q complement. The third input of gate N4 is Q. And this modified circuit inputs we are naming as J and K. Based on this, we are naming the flip-flop as JK flip-flop. So let's try to develop the truth table for this JK flip-flop. For any flip-flop, as and when the clock is 0, we are looking the next state is coming to be always the same as the previous state. Even we can verify even here also. Default, that is the case as I said for any flip-flop. Whenever the clock is 0, we are looking N3 and N4 both are 1. And having the preset is 1, clear is 1 for normal operation. If at all N1 output is X, N2 output is X complement before applying these inputs. So that X is the input of the N2, so N2 will continue the same X complement. N1 is having the input as X complement, so that N1 will continue with the X. It is giving a meaning, it is same as the previous state. The case with respect to any sort of flip-flop. And whenever clock is 1, it is possible to verify for 0, 0, as similar to the SR you can verify, it is coming to be Qn. For 0, 1, it is 0. For 1, 0, it is 1. And let's check because of 1, 1. So before applying clock signal, let us consider gate N1 output as a 1, N2 output as 0. Now while keeping J is 1, K is 1, if you apply the clock signal, for gate N3 and N4, out of 3 inputs, 2 inputs are 1. Out of 3 inputs, if at all we are looking 2 inputs are 1, then gate N3 and N4 outputs are depending upon the third input. So third input of gate N3 is Q complement. Third input of gate N4 is Q. So based on our assignment, Q complement is 0, Q is 1. Hence, having one of the input of the gate N3 is 0, N3 output is 1. Having all 3 inputs of the N4 are 1, N4 output is 0. So having one of the input of the gate N2 is 0, we can look to the NAND gate output without knowledge of other inputs. Having one of the input of the NAND gate is 1, or if the input of the NAND gate is 1, we can't read the NAND gate output without knowledge of the third input or the remaining inputs in general. So based on this, whenever we are having a situation like this, we are looking these two are in parallel. We need to look the output of the NAND gate which is having one of the input is 0. That NAND gate output we must read first. Hence, we are reading the NAND gate N2 first. One of the input of the N2 is 0, so that N2 output is 1. Now we are looking all the 3 inputs of N1 are 1, hence N1 output is 0. So having previous state as 1, we are able to read it is 0. As similar to this, if at all we are starting before applying the clock signal, if at all previous state is 0, it is possible to recognize the next state is coming to be 1. Hence, based on this, it is possible to speak whenever we are having J is 1, K is 1, while applying the clock signal, the next state we are going to read as a complement of the previous state. So it is the operation of this JK flip-flop. If at all we are looking the truth table of SR and JK flip-flop, in most of the textbooks you may be looking the truth tables simply like this: 0, 0, it is a Qn, 0, 1, it is 0, 1, 0, it is 1, 1, 1 is not load. Similarly for JK, 0 0 it is Qn, 0 1 0 1 0 it is 1 1 1 is a complement of the previous state. So for first three rows are concerned, the truth table of SR and JK are same. The SR flip-flop operation, JK flip-flop operation is differ with respect to only last row. Hence, if at all we are having a sequential circuit by using JK flip-flops, if you guarantee at any moment 1 1 inputs are not possible, then we are having a possibility to replace all these JK flip-flops even with the SR flip-flops. Condition is set, if at all we are looking at guarantee, in that circuit 1 1 inputs are not at all possible. Anyway, so most of the textbooks you will be looking to the truth tables like this. So whenever we are looking at truth table without this clock column, then default we need to understand the truth table is valid as and when we are applying a clock signal. And for these flip-flops, if you want to look to the symbolic representations, for SR flip-flop if at all we are looking, S or flip-flop Q complement, this is the preset, it is the clear and a clock purpose one more line. This is a SR flip-flop representation. Of course, we are naming it SR flip-flop. The reason, whenever we are reading S is 1 or is 0, the flip-flop output is 1. This operation we are naming as set operation. Whenever S is 0 or is 1, we are reading the flip-flop output is 0, that we are naming as reset operation. So basically, it is named as set reset flip-flop. In the abbreviated form, we are naming as SR flip-flop. As similar to this, if you want to look to the JK flip-flop truth table, it will be as it is. A small modification will be having inside the terminals. So the terminals are to be named here now as J and K. It is the only small modification required. And we are looking for preset and clear purpose, a bubble along with the line. It is a similar meaning of active low enable. We can understand here the effect of the preset we are having on the flip-flop whenever preset is 0. And effect of the clear we are having on the flip-flop whenever clear is 0. And based on this condition, for preset or clear operation, clear and preset are not the same value. Hence, other input default, it must be 1. So preset operation is whenever preset is 0, clear operation is whenever the clear is 0. To give that meaning, we are looking here, the symbolic representation for preset and clear, a line along with the bubble. So default consider, it's a part of the symbol. There is no any external components. Don't look any meaning, some NOT gates or something like that. Don't take any such meaning. It is a symbolic representation for this JK flip-flop or maybe for SR flip-flop. The meaning of what we said, logic 0 value effect with the preset and clear. For the study of the flip-flops, a part of the truth table, we need to talk on the flip-flop characteristic equation, and also we need to talk excitation table. So without this characteristic equation and excitation table, the study of the flip-flop will be incomplete if at all we are stopping just with the truth table. And if you look, what is this characteristic equation? We are using here a word, mathematical word equation. So character, the meaning, a grammatical meaning, if at all we are looking, it is nothing but talking about its behavior, its operation, or its nature. The operation, behavior, or nature of the flip-flops we are having already the study by using these truth tables. But based on this mathematical word, it is possible to understand if at all we are formatting this truth table data as a mathematical equation, that equation we suppose to name as characteristic equation. And we know that whenever we are developing an equation, in the mathematical sense if at all we are talking, whenever we are developing a mathematical equation, so in the mathematical equation we will be having always some independent variables and some dependent variables. So that to format this truth table as a mathematical equation, we need to understand what are the independent variables, what are the dependent variables. Basically, from the truth table, what information we are reading from the truth table about the flip-flops if at all we are looking. From the truth table, basically we are looking information about the next state of the flip-flop. So that the equation what we are going to develop, that's supposed to be on Qn plus 1. And this next state is depending upon which variables? The next state is depending upon the inputs of the flip-flops. So that Qn plus 1 is depending upon the inputs of the flip-flop. And also it is depends on the previous state of the circuit. So that it is also depend on the Qn. So that as and when we are developing a mathematical equation for Qn plus 1 as a function of inputs and Qn, such equation will be naming as the characteristic equation. So in general, it is a case with respect to any flip-flop. Let us try to develop first the characteristic equation for SR flip-flop. So when we are developing the characteristic equation for SR flip-flop, inputs are S and R. Hence we are going to develop an equation for Qn plus 1 as a function of S, R and Qn. To read this equation, we need to list first all possible values of S, R and Qn. So to read Qn plus 1, again it required for us to refer to only the truth table of the flip-flop. Whenever S is 0, R is 0, first two rows we are looking. The next state must be same as the previous state. So for this row, next state becomes 0 because the previous state is 0. For this row, the next state is 1 because the previous state is 1. And for next two rows we are looking S is 0, R is 1. Whenever S is 0, R is 1, the next state is 0. For next two rows, S is 1, R is 0. Whenever S is 1, R is 0, the next state is 1. Hence, the previous state may be anything, the next state is 1. And of course, 1, 1 is not allowed. So, from this table, we are looking the min terms for Qn plus 1 are 1, 4, 5. Don't cares, we are looking 6 and 7. And using K-map, if you simplify well, we will be looking here, it is S R with R bar Qn. It is coming to be S R with R bar Qn. If you check whether it is giving the same information of truth table or not, based on our discussion, it's supposed to give the same information of truth table. Suppose S is 0, R is 1, expected output, S is 0, R is 1, expected output is 0. So if you check for this, S is 0, R is 1, R is 1 means R complement is 0, we are looking here 0. If you check like this equation will be giving the same information, what information we are reading from the truth table. For possible input combination, it is going to give the same output what we are looking from the truth table. So this equation we are naming as the characteristic equation. As similar to this, now let's develop the characteristic equation for JK flip-flop. JK flip-flop is concerned, we need to read the next state Qn plus 1 as a function of J, K and Qn because inputs are now J and K. And without much efforts, we are having a possibility to use the same table. Just let us rename this. Instead of SR, let us use the names J and K. First 6 rows are concerned, that is 0 to 5. It is coming to be the same as the SR. Only with respect to the last 2 rows, we will be looking some changes. For 1 1, for JK flip-flop, the next state is the complement of the previous state. So for 1 1, the complement of the previous state means if it is 0, it is coming to be 1. If it is 1, it is coming to be 0. Hence, we are looking here. The min terms are 1, 4, 5 and 6. So by using truth table, by using K map, if you simplify, it is coming to be JQN bar R with K bar QN. It is the minimal expression what we can read. And as similar to the SR flip-flop, you can verify based on the possible values of J and K. If you check, it will give the same truth table what we are having. It will give the same information, the truth table, what we are looking from the truth table for possible J and K inputs. So it is the characteristic equation of this JK flip-flop. So like this, we will be developing for any flip-flop the characteristic equation. The next one, we are looking excitation table. On each and every flip-flop, we are looking some table as a truth table, and we need to have a question ourselves from the excitation table what information we want to read. So if we take this as a question, we can look to the meaning like this. If the present state of the circuit is X, while applying the clock signal, we want to read the next state is to be Y. To bring the circuit from this present state of X to Y, we need to bother what must be the inputs we need to apply. Such information we want to read from the excitation table. As we are talking, the present state of the flip-flop is X. While applying the clock signal, we want to bring the circuit from X to Y. To bring the flip-flop from X to Y, what must be the inputs of the flip-flop? So this information we want to read from the excitation table of the flip-flop. So based on this, it is possible to speak. The truth table will give the static information about the operation of the flip-flop, whereas the excitation table will give the dynamic information about the operation of the flip-flop. From the truth table, what we are looking, while applying so and so inputs, what the next state? It is a static nature, static behavior of the device. Whereas here we are talking about the transfer. Whenever we are talking about the transfer, it is generally about the dynamic behavior or dynamic operation of the circuit. So hence, it is possible to speak. The excitation table is talking the dynamic information, it is giving a dynamic information of the flip-flop, whereas the truth table is giving the static information about the operation of the flip-flop. The present state we used to write as a Qn. The next state will be giving as Qn plus 1. Let us try to develop the excitation table first for SR flip-flop. So we need to recognize what must be S and R inputs. And if you look here, the present state may be 0. If at all the present state is 0, the expected next state we may want to read the same 0, or the expected next state may want to read as 1. Similar to this, if at all the present state is 1, the expected next state may be 0, or the expected next state may be 1. So these are the possible transfers. On any flip-flop at all we are looking, these are the possible transfers. So for these possible transfers, we need to recognize what must be the inputs. So coming to the SR, we are looking what must be assigned or inputs. So this information also again we are reading while looking to the truth table of the flip-flop only. So for all these things, the basis is from the truth table. Anyway, if you look here, if you want to read the next state is to be 0, we are looking one possibility, S is 0, R is 1. And we are looking here, the next state is same as the previous state. From the truth table of SR, we are reading the next state, Qn plus 1, same as the previous state, that is Qn, whenever S is 0, R is 0. Hence, a part of 0, 1, we are having a possibility to apply even 0, 0. Hence, it is possible to speak now, to bring SR flip-flop from 0 to 0, S must be 0, or maybe any value. Similarly, if you look to the remaining 3, to read the flip-flop output, SR flip-flop output is to be 1. We are looking a possibility S must be 1, R must be 0. We are looking the next state is a complement to the previous state. In the SR flip-flop, we are not having any such input which is giving the next state as a complement to the previous state. So that to bring SR flip-flop from 0 to 1, it is only one possibility. That is S must be 1, R must be 0. And when we are talking 1 to 0 transfer, to read the 0 output, S must be 0, R must be 1. Here also we are looking the same problem. Next state is complement to the previous state. In the SR flip-flop, we are not having any such inputs. And coming to this 1 1, to read one output, we are looking one possibility 1 0. Next state is same as the previous state. In the SR flip-flop, the next state we are reading same as the previous state with 0 0 inputs. Hence, we are talking now to bring SR flip-flop 1 to 1, or must be 0, S may be any value. So like this, we are developing this table, and in a simple way, we will try to look this excitation table. For 0 to 0 transfer, 0 don't care. For 0 to 1 transfer, 1 0. For 1 to 0 transfer, 0 1. For 1 to 1 transfer, don't care, 0. So it's a thing what we need to remember. This excitation table, or in general excitation tables, we need to use very frequently while dealing with the synchronous sequential circuits. While designing synchronous sequential circuits, we need to use these excitation tables very frequently. Let us come to the excitation table of the JK flip-flop. So 0 to 0 transfer, to read the 0 output, J0, K1. Next state same as the previous state, hence we are having a possibility to apply even 0 0. So finally we are concluding, to bring the JK flip-flop 0 to 0, J must be 0, K may be of any value. Coming to 0 to 1, to read one output, one possibility 1 0. Next state complement to the previous state. In the JK flip-flop truth table, we are able to read the next state as a complement to the previous state whenever J is 1, K is 1. Hence, a part of 1 0, we are having a possibility to apply J1, K1. Hence, we are speaking now to bring the JK flip-flop 0 to 1, J must be 1, K may be any value. Coming to 1 to 0, to read the 0 output, one possibility is 0 1. Next state complement to the previous state, hence we can use even 1 1. From this, we are able to speak for 1 to 0 transfer, K must be 1, J may be of any value. To bring 1 to 1, to read one output, we are looking here. 1 0 is one possibility. Next state is same as the previous state. Even we can use a part of 1 0 0 0. Hence, we are able to speak to bring the JK flip-flop 1 to 1, K must be 0, J may be any value. So, we are consolidating this the JK flip-flop excitation table. We are able to speak here from this. For transfer 0 to 0, J must be 0, K may be of any value. For 0 to 1 transfer, J must be 1, K may be of any value. For 1 to 0 transfer, K must be 1, J may be of any value. For 1 to 1 transfer, K must be 0, J may be of any value. So, it is the excitation table of the JK flip-flop. Hence, to develop the excitation table of any flip-flop, while using the truth table, we need to work like this. While including this characteristic equation and excitation table apart the truth table, it becomes a complete study on any flip-flop. So that as and when we are having any flip-flop, we need to work for all these three.